Good morning, and thank you for joining today's webinar from SPEC Innovations, Product Lifecycle Management, and Model-Based Systems Engineering, Better Together. My name is Taylor Duffy, and I will be the moderator for today's webinar. First, I would like to go over some housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the Q&A part of the webinar. You can also interact with us on LinkedIn through the Innoslate users group or through Twitter using the handle @SPEC Innovations. The webinar is being recorded and will be made available to you after the live presentation, so keep an eye out for it in your inbox. Now, I would like to introduce you to our presenter, SPEC Innovations President and Founder, Dr. Stephen Dam. Dr. Dam has been involved with research, experiments, operations analysis, software development, systems engineering, and training for more than 40 years. He has also received an Expert Systems Engineering Professional ESEP certification from INCOSE. He is currently applying systems engineering techniques to various DoD, DOE, and commercial projects. Feel free to send him any questions through the LinkedIn users group or send him an email to steven.dam@specinnovations.com. And now I'll hand over the controls to Dr. Dan and we'll get started.
Thanks, Taylor. Appreciate it. So we'll go quickly over today's agenda. So first of all, I think we need to understand what is PLM. A lot of people have different perspectives on it. I went to the source. I went to Wikipedia. And then, of course, understanding MBSE. That's another key part of this is what is MBSE? What is it really doing? What are we trying to do with it? And I want to talk about how we've integrated these disciplines with Innoslate to tie it together to give you that full life cycle support you're looking for. And of course, we'll have time for Q&A. So let's talk about PLM first. So PLM combines 5 distinct disciplines. Systems engineering is one of those disciplines, of course, a very important one. Program management, which includes portfolio management. And then product design, of course. Process management for manufacturing. And product data management. So those are the ones, again, I pulled this right out of Wikipedia, so if it's wrong, sorry, it doesn't meet your definition, but it is the one that's up there, and most things up there are pretty good in terms of these kinds of definitions. So I do like to use it once in a while. So many practices focus on 1 or 2 of these disciplines in depth, but to be successful, you're really going to have to do all 5 areas. And of course, probably more. I mean, if you think about it, there's probably some stuff missing in there that we do. And then so we want to make sure we're managing the products through the whole life cycle, including disposal. And we often don't talk about that aspect of it, but that's all part of these processes as well. And so one of the things we did was a little bit more an in-depth analysis of the different disciplines that are associated. So this was a bit of work that was done some time ago, actually. In fact, you're going to see this is actually an earlier version of Innoslate. And looking at the tool features that we saw out there, it sort of showed how things were tied together. And this gives you a little bit of that flavor of the different aspects of it. So that further analysis says that there's really a number of sub-disciplines and products that you're looking for out of this. And of course, a complete PLM capability needs all these features, particularly the systems engineering part of this. It shows requirements management, but requirements management is more than simply the requirements piece of it, like cataloging requirements. It's deriving the requirements, it's analyzing the requirements, it's understanding the requirements, it's keeping the traceability of the requirements to the design and linking that all together. So there's a lot more, when we say requirements management, I mean, that's essentially what we're doing in systems engineering, but it's broader than that, really. And again, we have to produce deliverables in all these areas. And the whole idea is we want to be able to automate this as much as possible. Of course, to better understand the requirements, we really need to understand the lifecycle processes themselves. So what is it we need to be doing during the life cycle to execute PLM successfully? Well, there are many ways to visualize the life cycle. And I happen to like the V only because it's simple, it looks clean. people misinterpret it that the axis is a time axis. It's really more the steps that are occurring in the process. It can be executed in many different ways. If you look at it decompose, even like Agile, it has the same basic kinds of steps in it with that. So really fundamentally, it's just you're often talking about how much do we do in parallel, how much are we doing, iteratively, again, many ways to look at the V. So, but I like it again for simplicity, explaining the major steps in the process. And particularly, this is one that we've taken from the classic Moog and Forbes V diagram and added in that top bar, which is looking at the current operations and maintenance, future state, which are going to go to operations maintenance, and then disposal and demolition disposal. So D&D. Those are all part of that life cycle that often are forgotten about. So the classic V really is looking at only the development life cycle. It's not really looking at the full life cycle. So that's why we extended it the way we did. Now, we have found that there are processes that, you look at systems engineering cuts across the entire life cycle. There's roles for systems engineering throughout the life cycle. There's also program management throughout the life cycle. And so these are all things that will make it easier for you to see that breadth across. And of course, that's a lot of the job of the systems engineer, is to take and make sure that all the aspects of the system meet these needs through the entire life cycle, not just during the development process. It's not just getting the product out the door, it's making sure the product can be maintained. It can be supported as it's needed through logistics. And ultimately, it can be disposed of properly. So taking a look at those processes we've come up with coming down the V, basically we have during this design phase, there's the design analysis processes that we can use, again, classic systems engineering and program management types of things. If you do a top-down, that means someone's done a good job of creating a set of requirements or a fairly clear set of needs, and you at least be able to turn those into requirements fairly easily. What I found myself oftentimes is that I'll be on a project and they won't have a good set of requirements, but they have an existing system they want to replace. So what do I do there? Well, I do bottom up. I synthesize what's going on. I abstract the system components. I then think about functionally what are they doing, and then ultimately come up with a set of requirements. And this is, classic structured analysis, actually, is to do exactly that. But oftentimes I find myself in a situation where people don't really know what they want. And for that, I use functional analysis to help me understand what is the basic functions they're trying to perform. And if I can understand those business operations or warfighting operations in the DoD sense parlance, then I can understand, and I can create from that the requirements I need, and then from there develop the new systems that can do the job. So again, that just depends on where you are in the life cycle and what you need to do. Ultimately, out of each phase of the life cycle, if you're coming down that V, you're going to be creating specifications at each level, bills of materials, just all the information you need to ultimately to buy or build the products that you're trying to create. That you need to then begin to do the next phase, which is integration, right? So integration and verification coming up the V. First of all, one of the things that a lot of people don't realize is that there's a very important step while the design engineering is going on and those detailed work is being done, the software is being built, the system components are being built. The systems engineer needs to monitor that design activities to make sure that they can update the design information so that you can get an as built. This was one of the things back in the day. It was always a problem. Do I really have a good information on what the design really is? Not what I designed originally, but what did I really get? Okay, because they are two different things, and some people think they're supposed to be the same, but they're rarely the same. Because as you're doing design, particularly the detailed design, design engineers have all kinds of ideas to how to improve it, how to do things better, faster, cheaper, maybe make it more maintainable. Again, all those illities that you worry about, you're supposed to be worrying about up front, that often get ignored, frankly, even because of the hurriedness of the design process. So by thinking about those through the life cycle, you want to make sure you're capturing that. So that design monitoring phase is really important. And of course, integration verification there is then to be making sure that are the requirements being met. And of course, if you're doing the correct thing in the V, you've set these up. You have done work on that coming down the V that you ready for doing all that IV and V planning should have been occurring all the way during the beginning of the life cycle and all the way through. If most people don't realize, but for phase A, milestone A in DoD, in the DoD 5000, it says you're supposed to have a test and evaluation master plan. How many people have a complete test and evaluation master plan at milestone A? Not enough. So there's too many TBDs often in those kinds of documents, and they need to be clearer. So that's something we're pushing towards these days, trying to see if we can't improve that. The key is customer satisfaction, and transition to operations as a key part of these steps. So again, we're wanting to make sure that we're really preparing the customer or the end user as well. So there may be two different groups of people for what they're going to get. So, the best surprise is no surprise. That old Holiday Inn commercial, it's still true. The customers don't want to be surprised. They want to be happy with what they've got and know what to do with it and be ready to use it. So again, particularly with design processes often taking a long time, there's changes in the customers and the user community, and of course, if you're in DoD, the threat changes constantly. So again, the world you go into is a different state than what you started in. Okay, so understanding model-based systems engineering. So we kind of got PLM, hopefully understanding and looking at the whole life cycle and what we're doing there and how that's important. So understanding MBSE. So first of all, the definition from NCOSE is this, and you read it, and it's definitely got the whole life cycle in there, talking about it throughout. In fact, the words life cycle show up, right, explicitly. So it really is meant to try to work the whole breadth of the systems engineering, at least for the life cycle. Now, most of us who've been working in this business for a long time have been basically doing modeling as part of how we do systems engineering. I mean, frankly, I've been doing it for my entire career, which spans over 40 years. And so, how is this different? So it's often a question that gets asked, and certainly, it's something that we need to address. So let's understand what MBSE is. So MBSE includes a number of disciplines, right? Again, it says it's systems engineering, I should say. It requires a number of disciplines: requirements analysis management. We've talked about just about all these already. And again, V&V is part of that systems engineering process. Don't, just because you're a test engineer, you're actually a systems engineer doing test or doing V&V work. So you have the same skill set. You need to have that same skill set to do that, actually. And now also program management, what's added in the program management piece of this. So again, the systems engineer and program managers work together. Oftentimes they may even be the same person doing both jobs. Certainly had that position thrust on me several times through my career. And so the key is you're trying to optimize cost, schedule, performance, and mitigate risk. I didn't mention that here, but risk is a portion of that. You're trying to keep the risk to a level that is acceptable. And then the systems engineer does that for the system, and the program manager does it for the program. And the two are a little different, right? Because the program, I'm worried about the cost and schedule of the program itself and how long that's going to take, and can I meet my schedules and get this product out when I need it. But for the systems engineer, they're looking at the cost and schedule of the system itself. How much is it going to cost by itself? That information, the program manager is not going to come up with that information. It's the systems engineering who has to estimate how much these components are going to cost. Also the schedule, when can they be delivered? What's their technology readiness levels? You know, particularly if I'm doing technology development or R&D at the same time, which we often are, yeah, that schedule thing is really important. we want to make sure we've done that. And the problem often happens to us is the cost and schedule get locked in early in the life cycle. Those decisions get made oftentimes way too early in the life cycle, and the final cost and schedule. And so what happens then is the only factor you have to work with is performance or risk. And again, you know, most people don't really, you know, because the risk is all kinds of forms of the risk, right? So again, both for the program and the systems, and the risk is different between the two. So again, that's something we want to track. So the main difference between systems engineering and model-based systems engineering is the idea that you're using these modern software tools to capture data in a repository and convert this data into information through analysis and visualizations. Okay, so when I think about that, what does that really mean? That means I've been doing this my entire career. I've been using these tools to do this because doing it by hand to me was painful. I was of the era before we had personal computers, and I saw what it took to do systems engineering manually, and I thought that was crazy. And we have modern computers. Why can't we capture the information in the computers and be able to use that to help develop our documentation? So yes, that's what we should be doing. Now, one of the things that you see a lot is a lot of people equate systems engineering with model-based systems engineering, and even with SysML. Okay, but the actual relationship is systems engineering is a superset or equal to MBSE, depending how you practice your MBSE. But MBSE is definitely a superset of SysML, because SysML doesn't have the cost, the schedule, the risk factors defined. Now, can you put them into your tools? Absolutely. That's not the issue. The issue is the standard doesn't do that. And if the standard doesn't do it, we're all going to do it differently. And that's part of that interoperability problem we keep running into. So let's go understanding MBSE a little more. So what's the benefits of models? So first of all, models provide traceability in many dimensions. You know, a lot of people talk about requirements traceability. It ain't just the requirements, people. It's everything. You're connecting all this information together, and it all connects together in a way that you have many dimensions of the problem. Okay, so this isn't one or two dimensional problem. This is a 20-dimensional problem at least, if not more. So when you think about the problem, that traceability is what keeps things connected to each other, and that's why bidirectional traceability is very important. Because again, that top down, bottom up, middle out, I may start from any point when I'm doing my systems engineering process. I've got to have the traceability in each direction. And so again, this is where my tools can help me a lot if they do that. Also, you can use models can help you use and make sure that rules are being met. You can use simulation to execute your behavioral models, for example, things like that to help you even derive performance. I've used those for years now to derive performance factors, performance requirements for the system. So if you say how long something needs to occur, I can start using that to start looking at some of those performance timing information. I can use it to look at resources and resource usage. So that just a lot of ways you can look at performance in this as well. Models can be interrogated. You can easily be able to go through the model, find different pieces of information. Again, if they're linked together through the traceability as well, that's again part of the model. So again, if you're thinking model, we're thinking about data here. We're not talking about pictures. When I talk about model, I don't mean just pictures. I mean all the data associated with the information you need to describe the system and the program. And of course, models can be reused. That's very helpful, okay? Because again, we do a lot of the same kinds of things. We may not do the same thing every time. I mean, once you do that, you're really kind of in the manufacturing world, and you are doing just the same thing. I mean, even the car companies, they're reinventing these cars constantly. I know it's evolutionary to a certain extent, but there's some revolutions here and there. And it's important that you recognize that part of it. So again, reusing the models is, as much as you can, is very valuable. And of course, models can be easily changed. That's important. So again, you're always going to be changing things. You're always going to be adjusting things. You're always going to be learning, and you want to be able to capture those lessons learned and really be able to learn them. And that change ability, that ability to track changes and control change is very, very important in your modeling. Okay, so given that we kind of now understand what PLM and MBSE are, let's talk about Innoslate and how it helps with this. So Innoslate provides a complete systems engineering environment, and which we think it really improves PLM. So if you're using PLM with some other tools and things like that, and there's other tools that do make sense to use with it, then that's fine. But most of them are very weak in the systems engineering domain. And so you want to use a strong systems engineering tool. And of course, Innoslate is not just a systems engineering tool. It's really a systems engineering and program management tool, since it does bring in all of the other kinds of things, which we're going to talk about more in a second. But the systems engineering part of it, dashboards, of course, are a lot of that communications that we have to do as systems engineers. We want to make sure we have an easy way for people to look at the information and be able to gravitate to it and find out the things they need to do. The documents view, which includes requirements documents, ConOps, all your plans, reports, all that can be captured in it too. Again, as a living document, not as a PowerPoint or a PDF or a Word file. This is now objects in the database. You can reuse, you can trace. It gives you so much more that you can work with than just a static document type or a SharePoint. Google Docs or things like that, which are great. But again, for what we want to do in terms of systems engineering, we need that traceability, and that doesn't happen easily with those other kinds of tools. But there really are production tools that are really meant to produce documentation. Functional and physical diagrams. So it has all kinds of diagrams. The diagrams dashboard here shows a number of different types here. Of course, all the SysML diagrams are part of this. That's always important to make sure we provide this in any form. There's 26 diagram types, and there's also a charts view, which has 5 chart types. So lots of different ways to see the information that you need to capture and work with it. Another thing is there's a built-in discrete event and Monte Carlo simulation. Now, if you're not using Monte Carlo simulation, you probably aren't really doing enough systems engineering. Because particularly early in the design phase, we don't know most of these numbers very well at all. In fact, kind of guessing what a lot of the numbers might be for parameters, sizes of things, or the cost of something. All these factors you think about. Oftentimes, we do what we call engineering judgment. We come up with a number, right? Well, actually, what we usually do though is we say, well, the best case is it's this value. The worst case is it's that value, but it's most likely going to be this value, right? So you got 3 points. Well, that makes a nice triangular distribution. And if you can put that information into the modeling, you can use it to help you estimate and get a feeling for what your risk might be and things like that as well. So again, that simulation ability to start understanding those distributions and what might be there. And as you go over time and you measure things better and you get real distributions, you can apply real distributions. Of course, that's what you want to do. But also, you need a way to do V&V. Okay, so V&V, again, is a critical part of systems engineering. It's not separate. It's not some other discipline. It's part of systems engineering. Okay, at least that's the way Incosi defines it. And I agree with Incosi on that one. So we have a test center. So for that, now we call it test center rather than V&V center. You know, again, people get confused. Yes, you can use it for your analyses as well as testing. But we call them test cases, but it doesn't matter what you call it. It's really the same thing. And so use it as you need to. You can track all what you're doing in it. We currently use Test Center for our own development work, but we have 10,000 automated tests that we run in a tool called Selenium. And our test cases are all in Innoslate. And so as Selenium executes, we update the values of the test cases, the status. Now, we used to do that status tracking in a spreadsheet. It took us days to track what was happening on a test. This is then, as each test is run, your status is updated immediately. You know exactly what's going on. So you imagine the cost reduction that is, the time reduction that is, in terms of being able to turn things around and improve our testing. Another thing we do is, of course, program management information. So again, you can model your processes. So again, our action diagram or activity diagram can be used to model processes. And you probably do that all the time, right? Well, why not do those for your project processes as well? And you can track those things. And we have little input outputs, which can represent the reports or the outputs or the inputs to a particular phase of the process. So again, it's a great way to do it. It's a great way to model your actual work processes. You can create work breakdown structures as well. So those are just hierarchies of the work. So again, we have hierarchy diagrams, different classes of information for that. Capturing decisions. Now that's one of the things, again, often ignored. It's one of those things that we're not supposed to ignore. In fact, by law, the Department of Defense is supposed to be creating decision databases, and they do. But a lot of times we don't feed those decision databases very well. And so, in capturing those decisions through the process of the project, why were those changes made? What happened? Why did this not work? You know, that'll help you later on when you're trying to do your lessons learned and really learn your lessons. Of course, identifying and managing risk, very important. We have a risk matrix that uses probability and consequence as its main types of way to define risk as the product of those two values. We also have the ability to do a risk burn down chart. So you have that capability as well. So again, we do a very nice job of risk. You can set up your risk register in our database view very easily and see what's my risk, what's it mitigated by, what's that cost. Again, all that information can be captured and put together in one place. Easy, easy, easy. We have now, if you're into time, and I am, I'm very time constrained as a person in my life, and I find myself having to constantly track things in time. So we give you Gantt charts, Kanban boards, timeline diagrams. I think there's even a calendar in one of the program manager's dashboard. So, and of course, cost is another aspect of that. Very, very important factor. And of course, we do have interoperability with Microsoft Project as well as the other Office things. So again, when you go to publication and you need to go to something else, or you want to do EVMS, for example, again, many people are not really doing EVMS, they're doing it. It's really a trailing indicator. So a lot of people are kind of walking away from EVMS. So I don't know if you're a big EVMS fan, but it really, it's unclear how much it helps. So again, something we're looking to add into Innoslate at some point in time. But I think that's the only thing we're missing from Microsoft Project that you might need to use Project for. Product design. Of course, that's an important aspect of it. Now, we're not a CAD tool, and we don't want to be a CAD tool. There are great CAD tools out there. Oh my gosh, SolidWorks is fantastic. Of course, the Autodesk was the originator. Many others. There's Space Claim by ANSYS that we've used, and very nice capability there. And many of those, by the way, can go right to computer-aided manufacturing, particularly additive manufacturing. And so that's very cool. But our job as systems engineers is to understand that work. Again, this is part of that design monitoring, and curate the data. So we want to take the results and make sure we have it someplace. So in Innoslate, what you do is you upload the CAD file as an artifact in the database. That's one of our classes. And then we have a CAD viewer that if it's a CAD type that we can view, we have a viewer for you to be able to see it. So there's a nice color picture of a car that's there. If you want to also do some more detailed analysis, you want to be able to capture other things, you can decompose, I think it's the .obj file. And so if you have that, you can do a decomposition. So this is the hierarchy chart down here is a shuttle, the old space shuttle, and basically had some different aspects of it that were in that particular CAD file. So again, it'd be a way to help you do more detailed design. So maybe you have a more detailed file for the wings you'd want to tie to it. So again, you could link that to it and see it that way. Or this can help you with your modeling and make sure you're tracking and that they kind of follow the same kind of things you had in your basic design, or update the design aspects too. So again, this can help you do some analysis. Another thing, of course, is make sure you do test plans and capture test results. And again, as I mentioned, we have both the documents view for test plan development and also with the test center for your testing results. Okay, so another one was, of course, manufacturing processes. Those are very important. We can model and verify through simulation. With the APIs, you can link them to MPM tools. So if you've got actual processing tools, there's ways to do that. We have conducted failure modes, effects, criticality analyses, FMICAs, with it. That's actually fairly easy to do. Again, it's a modeling process. We also do have state transition diagrams. So if you do want to model your states and modes, I will say that I found that I'll model the states and modes as a state diagram just to get the kind of big picture. But to actually do execution, I want to use the behavioral diagram because I can do more with it in terms of particularly the resource usage. That's a key part of what we're doing with it, and make sure we have that. The triggering using input outputs. It's a cleaner way of seeing the entire process and making sure I have the entire functionality, which is the purpose of these diagrams, by the way, is to identify my underlying functional requirements and functionality of the system. A lot of people don't know why they're really diagramming. You're diagramming to do primarily that in the behavioral modeling part of it. Now, of course, the physical modeling part, you're trying to get a handle on, what is it, the real state of the system physically. And again, we have some great integrations with design engineering tools. We work with STK and MATLAB, that's co-simulations and our discrete event simulator. GitHub, we have a software integration there that we use a round trip with GitHub, where we actually have a GitHub viewer where you can go in and view what's going on in your GitHub repository. You can also then push issues down to it. They call them issues, we call them requirements, right? In the software world, they call it issues. And so they do their issue tracking in GitHub. And then because we've created a link between the two tools, as they make changes and do updates, we get the results updated in Innoslate. So again, that gives you that round trip capability. Again, I mentioned already the CAD viewer and Selenium, so I mentioned those. One of the cool things too that's been kind of fun is that we can use the AR/VR tools like the HoloLens. And particularly the HoloLens is really good because it's a browser-based tool. And so since we work on any browser, It's easy to interface with it, and we have very nice touch work with now. Particularly, I use it on my iPad all the time. So the HoloLens works fairly nicely now with it, particularly the upgraded software they have. We also have generative AI. Currently, we're supporting ChatGPT. I think it's version 4.0. And we are expanding that capability to get a more secure generative AI capabilities so you can provide your own firewall. And that's, again, we think is a key future capability, future technology that we want to make sure we can apply to systems engineering effectively. Project data management. Oh my gosh. So there's lots of ways to capture data in it. One of the things, we have a schema editor. So again, if we are not capturing all the data elements you want, it's easy to add the schema, add it to the schema. So here's a couple examples here where, well, the first one shows just a work breakdown structure and shows it in the hierarchy chart. We can show the attributes, values, and also labels that are associated with it. So again, that's a nice way to track things. Down the bottom right is a thing where we're looking at some cables and their particular types and values and parts and part numbers and on and on. You can capture all that information that you need in a tabular kind of view. But again, these are objects in a database. They're all related to each other. They again are reusable, traceable. I can easily tie it to other things. It just gives you more complete capability. Also, you can curate things like supplier vendor information, material data sheets, things like that. Again, as you need them. Again, those could be artifacts, or maybe those are specific pieces of information and data I want to add to it. You certainly can define that easily to do that. Again, I think I mentioned both the schema editor and the artifacts. Again, and work breakdown structures, and of course, bills of material, because again, we have cost associated with it. So again, as you need your cost information, link it all together in one place. By the way, your CAD drawings will give you some of that, and you get some of that information from there, but you won't get the whole system. If you want a full work breakdown structure and bill of material for the entire system, you can't get that from a CAD tool alone. So you need to have another place to take that CAD information and bring it up to the systems level and program level, and that's what Innoslate provides. Real-time collaboration. So another thing that we designed the tool for was we work in teams. We all do. I mean, we're on Microsoft Teams, right? So we work in teams and we work with each other and we do all kinds of things. And we want to have some way to be able to talk to each other, communicate, identify when we're working on the same thing at the same time. We don't want this check-in, check-out of databases. That just gets to be very confusing and problematic. We do track history, by the way. So if you do need to revert back to a previous version because somebody changed something you didn't want changed, that's okay. But again, if you've given them access to your project, your Innoslate project, you want them to be able to make changes in your project. If you don't trust them enough to make changes in your project, give them their own project, and then they can do everything they need to do in there, and you can subsume that information to your project using cross-project relationships. So again, you don't have to duplicate information. Our traceability can be between Innoslate projects. Okay, so you can think of now. I might have. In fact, we did this for a Navy project. We had different components of the system, and each one of them had their own Innoslate project where they were working in. And then at the systems level, we integrated the bigger pieces together for that bigger picture. And that way we could track and see what they were doing. We had interface standards we could track and things like that. So really made it much more efficient and effective. With this collaboration, we have real-time indicators when somebody else is looking at the same object you are. There's a group chat, private chat capability as well. And there are project notifications, which is that bottom right corner's picture. Okay, we have not quite done yet. So we did scale the tool. So we tested this to millions of objects. I think it's 10 million objects and 500 simultaneous users. So I believe that's our current testing regime. This was some of the particular testing we did. So, but just having that on the back end, it's really important to have that responsiveness. And so one of the things we've done is institute infinite scrolling in a lot of places. So our documents view, instead of loading the entire document at once, and if you've seen this, if you use Microsoft Word, they load the entire document in. If you have a very large document, like a 100-page, 200-page document, it can take a while for that to happen. So the infinite scrolling gives us that ability to manage very, very large documents. I forget what we've tested to, but it's very, very large. So again, we're doing things like that in the software itself. But the back-end hardware really depends on where you're running it. And we're cloud native, so we can do the virtualized cloud servers. You know, if you're using services like Google, they auto scale. And so, you know, most of the others don't really auto scale fully. They all have a limit. But you know, that's where we're trying to get to in the industry. So that's coming. Of course, it's easy to use. There's a lot of drag and drop. There's sidebars for attributes instead of modals to block what you're looking at. That's very helpful, particularly if you're in a diagram and you're looking at, you want to interrogate one of the objects in the diagram. You want to see all its attributes and relationships and things like that, or make a comment. This lets you do that again on the side, so it's out of the way. I can't tell you what a productivity that is by itself. In the documents view, by the way, we also have a hierarchy chart where you can go and use that to navigate, but also you can use it to drag and drop sections. So the little up and down arrows in there, if you don't know what those are actually lets you move different sections. So you can move major parts of a document around as you need to in a very large document. So this again is something that's very powerful. That help it. Again, this is because it's a modern tool written to all the latest web software standards. We have had re-architectures of the tool to take advantage of these capabilities. So if you don't know our versioning number, the first version number is the architecture version number, and we're at 4.11 is under development right now. And so 4.10 is the current release. So that means we've re-architected the tool since we first released 3 times. Again, that's considered best practices. So PLM plus MBSE leads to data-driven systems engineering and digital engineering. Okay, so when you think about it, PLM and MBSE are kind of how we used to talk about the life cycle, and I know a lot of people still are using those terms, and that's fine. But you know, the new vogue term is digital engineering, and the idea is this brings all of our tools and processes together to support the entire life cycle. And so that's something that a powerful concept. And to go with that, we've realized that models have been focused on diagrams, and that doesn't really quite do what we want. We're really looking to understand the underlying data. And so we're and a group of us in the lifecycle modeling organization have come up with this idea of calling it data-driven systems engineering. We've done a number of presentations and papers on that. The idea there is using a semantic ontology to meet the needs, that common language for digital engineering. So again, if you want to know a little more about that, check it out at lifecyclemodeling.org. And I think we got a couple minutes, enough that I can play this video. So this will give you a little bit of a feeling for what we're doing in terms of the full life cycle. Our team of systems engineers have responded to the NASA Break the Ice Lunar Challenge. They developed a lunar rover that can break the ice using a digital engineering approach. The challenge is to find solutions for excavating regolith, maximizing water delivered, minimizing mass of equipment, and minimizing power consumption. The goal of the challenge is to extract 10,000 kilograms of water from the regolith in 365 days.
The rover is important because as a part of SPEC Innovations, we provide our own cloud-based software tools to support system engineering as well as digital thread itself.
Innoslate integrates all the tools together to create a single source of truth for the entire system. This is where digital twin lives. Everybody's been talking about it, Nobody's actually really done it. And the best way for us to do that was to create a demonstration to show how all this could come together in one place.
Essentially, every capability, component, and integration with Innoslate has been included in this Lunar Rover project. That includes every view, tool, and partnership. To be more specific, project initiation and planning utilize the documents, diagrams, and task management views. Task 1 incorporated the same views and utilized modeling and simulation and the database CAD viewer and equation editor in order to research and design the Lunar Rover prototype. Task 2 exemplified integrations with GitHub, SDK, and MATLAB through SPEC's partnerships with those tools for building the Lunar Rover prototype. Task 3 utilized Innoslate's test center and incorporated Innoslate's integrations with LabVIEW and ANSYS for testing the Lunar Rover prototype. At the end of this project, an end-to-end complete digital thread showcased in Innoslate.
Through the integration of Innoslate, ANSYS, AGI, SDK, GitHub, and other tools, we've built a Lunar Rover. The digital twin continues to receive information from its physical twin to keep them in sync. And so this has given us an opportunity to show that capability in a way that otherwise we never could. So before they go to another video on me, here's the link for that YouTube video. You can watch yourself. Also, we have more detail if you want to see more about that. This was done quite a number of years ago, actually. So about 4 or 5 years ago now. And so I think when I said at the time that people hadn't done it, I think people are doing it now. And so I'm kind of excited about that and seeing that people have caught up this idea of getting the digital twin and making it work. So let me go to the next slide here. And so if you want more information, please contact sales and or also contact us at the SPEC Innovations. Highly recommend checking out our website. The resources page is full of things to help you find information and help you build models. We have reference architectures. There's a digital curation station, all kinds of information, and books you can download for free, including a book for kids. So highly recommend going and checking that out. Okay, so do we have time for some questions? Taylor, do we have any questions?
Yeah, we've received several already. If you haven't done so, please send your questions through the panel on the right that pops up after clicking Q&A on the top bar. He will answer as many questions as he can before our time is up. This first one came from the chat. Do you need to know SysML to use Innoslate?
No, not at all. In fact, I was realizing the other day I've never purposely created a SysML diagram. In fact, we find that we can do it very easily. But of course, if you want to use SysML, we have all that capability in the tools, so you have both. But we think we've got a fairly much easier way to do it. So again, that's in my book, Real MBSE, if you want to read that. Next question.
Any integrations or examples with BIM tools beyond just CAD tools, verifying requirements in design with federated models and Navisworks, for example?
Yeah, so we have not done that ourselves. Some of our partners have, some of our customers have, I know. And so that's certainly feasible to do, but it's not something that's in our area of expertise. So we haven't done it ourselves. Now, if someone wants to share doing that or wants to even come pay us to do that, we're happy to go do that and see if we can't make that work, be more effective for you.
Great.
Next question.
How is MBSE different from the standard systems engineering many people have done for decades?
Well, see, I don't think it should be. The only real difference is we've mechanized it. It's really using the computers more effectively to capture the information that we're supposed to be doing in systems engineering. That's why I said, systems engineering is either a superset of MBSE or it's equal to MBSE. It just depends how you practice MBSE. And that's the key. But yeah, no, again, I've been doing it this way for many years. It's new to a lot of people. A lot of people are still in Microsoft Office. That's people ask, well, who's our big competitor? I say Microsoft Office, because that's who our number one competitor is. That's who most people are using still, because that's what's on their desktop. So Next question.
When mentioning the term digital twin, do you link it to the Microsoft Digital Twin Definition Language, DTDL, or to the Europe-based Asset Administration Shell, AAS?
So I'm not that familiar with either one of those two, so it's hard. I'm not sure I link it to anything. It's more about, are you really capturing the information that accurately enough? Because we have to remember our models are always abstractions of the reality, and you try to make them as close as you can. And particularly as you get later in the life cycle, as you get real data on the real object, you can calibrate your models to a point where now they can even help you become more predictive. And of course, if you now take this, and the whole idea of digital engineering is taking it not only one life cycle, but you're going to do it again for the next life cycle and the next life cycle, and you're going to take those same models and enhance them and improve them over time. So eventually you get closer and closer to what people are looking for, which is towards the identical twin and not the fraternal twin, which is what most of us really have right now. So again, I'm not that familiar with those specific languages, but I sure would like to check up. We'll have to check them out. Next question.
This came from the chat. Would you be willing to have an informal call where we can discuss BIM tool integration with SPEC or Innoslate based on your response?
Oh, of course. Yeah, we're happy to try to integrate with anybody. We have a very open platform. It was designed to be open. And we want to encourage that interoperability between tools. Part of why we did what we did was to try to encourage that interoperability. Next
Great.
slide.
And they followed up with, how about integration with dedicated PLM tools like Aris, Dassault, 3D Experience,
Sure.
CATIA, or Magic?
Oh, we'd be happy to integrate with anybody. Whatever makes sense to do, it's perfectly fine. We want particularly customers to be able to do their job. That's our goal. So whatever we can do to help them do their job better, I'm all for it.
Awesome. Is Innoslate really a PLM tool? It doesn't seem to have all the components of PLM.
I don't think it has all the components. I wouldn't call it a PLM tool per se, except that it's a PLM tool at the higher level, in the sense that what it's doing is it's capturing that entire product lifecycle information set that you need. What it doesn't have is the CAD, CAM kind of direct interaction. But again, the CAD tools do this already. So do I want to? Do I want that? The manufacturing processes, again, I have seen people using BPMN to help automate those processes. I don't know why we couldn't generate the same kind of information set for that. But again, it's not been what we've been doing ourselves. So it's been a little hard for us to extend it to all those other things. But again, very open to doing that and making that capability. But again, that's where tying it to another PLM tool makes good sense. I think we're all kind of doing just a piece of the puzzle. We're not doing the whole puzzle that's needed. That's at least what I've sensed.
Great. One last question. How does the lifecycle modeling language support PLM?
So LML was designed to support the entire life cycle. And it really was trying to bring together particularly the systems engineering and program management parts together. To tie it now to the CAD, it's unclear how to do that exactly, except through what the mechanism we're using right now. And so again, this is where we separate between what we call the systems level tools and the design engineering level tools. So if you look at the V, usually people will put a line right in, not in the middle of it, but sort of at that bottom layer of the V, and the top part is your systems all the way up to mission level, campaign level kinds of modeling and analyses and things like that. And then below that line is the design engineering. So that's where you're doing the detailed electrical engineering, mechanical engineering, using those kind of tools for that work, software engineering, on and on. And so, but you have to have some way to bring that back up to that systems level and be able to, so the users and the people who are paying the money can actually understand what's going on and see the results and see how it's working. And so LML facilitates that through the language, and it's extensible as you need it to be as well.
Thanks, Steve. You could go to the next slide. I'll close this out. We would like to thank you again for joining us today. As a reminder, we'll be following up with you very soon to send you a link to the recording and the presentation slide deck. We hope you can join us for next month's webinar, Leading the Digital Transformation with Innoslate, on Tuesday, December 17th. Your link to sign up will be in the email that is coming soon to your mailbox with the slides and recording. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day, and we hope to see you at our next webinar.